Hi, good morning everyone. So in this video what I'm going to do is actually first give you a summary of work. I'm not going to go over power because that's kind of separate from today's lesson. Power is the amount of energy you use per time. That's the nitty-gritty of it. But I will do a little bit about what work is because we're going to apply it to the concept of conservation of energy. So, work. So work kind of looks at two things. It looks at force times a distance. So what we learned in class is that if I took an object and say I want it to start here, this is the starting point, and I want it to go here, that the way I apply a force matters. If I want it to go here, call this distance d, and I apply a force in the most kind of obvious sense in the direction of where I want to go, we'll find that the object will go to that location. So a very simple example is if I take this tape and I want it to go forward, and if I push it forward, it goes forward. I know that's a really silly thing, but in physics we say that force was really effective at pushing that object in that direction. In fact, when force and distance are going together, we say that's positive work, and we've added energy to the system. And right now, I'm going to define as adding energy as going from not moving to moving, okay? So it looks more energetic this way. So I know it's a kind of a simple definition of energy, but we're saying we're adding energy. This thing is now sped up. And that's an add of energy. We have positive work. So there's actually another kind of work, which is called negative work. So same scenario, if I start here, this is where I started, and I end over here. Say I want to go this way, my distance d like this, but let's say the force acts against you. Friction is one big example. We get a friction acting against us like this. So just to give you a visual demonstration, I know you can't see on the video, but we're here in class, right? If I push this, and once I let go, we see it slows down, right? It comes to stop. And the reason is, once my force is gone, the only force that's acting on it is friction. We can see the object slows down in this case. So here's a case where we're going to say this is negative work. If you notice, the direction of the arrows matter. If they're opposite, it's negative work. If they're together, they're positive work. This slows down, and we lose energy here. So work tells us a little bit about the change of energy. Are you gaining energy or are you losing energy? So that's how work and energy are kind of connected here. I could do one more quick example. You'll have to watch the videos for more examples and more details, but this is all you need for today's lesson to understand what I'm going to talk about. Same scenario. If I wanted to start here and end in that same spot, d, my distance where I want it to go, I could push, of course I could push this in many different ways. I could actually push straight down on this. And it's not exciting, but what do you see happening? Nothing, right? Does it move? No. Okay? So the way you apply a force matters. You know, you can't just apply it any way. You kind of knew that through intuition. But if I apply a force straight down, like this, then we say no work is done. Because we're not moving this object. The object's force is not effective at moving this object. So there is no change in the object's motion. And we could call that constant speed, right? I mean, even rest is a constant speed. when there is no work on your system, there's no change in our energy either. So notice that if I push down on this, there's nothing happening. There's no change in energy. Can someone grab the door in the back? Thanks. So in summary, we can add work to a system. We can have positive work, which adds energy. We can have negative work, which takes away energy. And we could have no work, which doesn't do anything to the energy. So with that said, well, hold that thought. Another quick thing, so that's all about work. I'm going to quickly segue to talk about recognizing types of energy. This is a quick review. Things that move have what's called kinetic energy. Have you heard that before? Some of you? So things that move will have a form of energy called kinetic energy. So the faster you move, the more energy you have. So these are types of energy. This is the other lesson. Just summarizing here. Lots of details in the lesson. We also have energy associated with lifting an object against gravity. So if you start here and end here, and you have a change of height, you have what is called gravitational potential energy. I think you might have heard of that, potential energy, maybe in middle school. It's been a while. So that's another form of energy, thank you, called gravitational potential energy, and that's based on change of position with height. So you're changing this. This is motion. And there's another form of energy called elastic energy. Which has to do with a stretch of a spring. So if you take a spring and you stretch it some distance x, you have elastic energy. So stretching a spring, there's energy in it. So if you pull back a bow and arrow, you kind of know that if you take a bow and arrow and you pull it back, and then you release it, all that energy from stretching it goes into shooting a bow and arrow, or the arrow in this case, or whatever you have there. Yeah?
Is it the energy like when you pull it or after you release it?
Pull it. So this is the pulling energy. Great. So there's pulling energy, like pulling something elastic, rubbery. So it could be a rubber band, it could be a hair elastic, anything that you can stretch. This has to do with height. So hills, like standing on a hill, you have energy, strangely enough. So anything associated with height. And this, of course, associated with motion anytime you move. That is a huge, brief summary on the types of energy. Now I'm going to take everything I just talked about and put it together. Called conservation of energy. Everyone all set, or you need a minute? All set? Okay. So like I said, you'll have details of all this. There you go. All right, and here's our major concept today that I'm going to teach, which is called conservation of energy. So basically, I'm going to say a few different phrases. These are some of your textbook information, and then I'm going to translate them, kind of like I did for Newton's laws. Like, this is what Newton's law says, but this is what it actually means. So, first of all, TME means total mechanical energy. So, let me go back here and just annotate this. So TME, total mechanical energy. So first of all, mechanical energy is what I just listed before. So those are types of mechanical energy. So those were the kinetic energy, gravitational potential, and elastic. Those are all forms of mechanical energy, things that move, okay? Things that are not mechanical energy include like chemical energy, so all the stuff you do in chemistry is chemical energy, that's not mechanical. Electrical energy, so energy associated with electricity, that's not mechanical. I'll just tell you that we're only using mechanical energy during this unit. There's no other types of energy. Second, the word total means what, mathematically? Yeah, sum. Sorry, I was meant for this. I'll fix that. There we go. That's better. Sum. So, it means that the total energies that you have existing in a system is always conserved. So, conserved means the same. Or sustained. Conserved means the same. As long as there is no outside work. So work has to equal 0 for this condition to exist. So for instance, when I push straight down on this masking tape or this tape measure right here, I'm technically conserving energy because no work's done in the system. No work. Strangely enough, all energy is conserved in the universe. So the universe, for example, will start with 4 units of energy, and all of time will always be 4 units of energy. Which means we can never create new energy or get rid of old energy. So when you say you make electricity, for example, they're not actually making electricity, they're just taking the energy from something else. So in order to make the electrons move up here, they have to actually take that energy, for example, from waterfalls. That's a common example. If you notice, power plants are near waterfalls because the water will fall, which has potential energy, goes into kinetic energy, spins a magnet. That's a simple way of making electricity. That magnet moves electrons. That's how it works. So you have to get that energy from somewhere else. Coal heats up water to spin the turbines, so that's why people burn coal for energy production. Natural gas does the same thing. They heat water to use the steam to spin turbines. Nuclear power is the same thing. It heats water by doing chemical reactions, makes steam, moves a turbine. That's all power. Anyway, the whole point I'm making is it's not generated, it's taken from somewhere else. So you cannot create or destroy it. So I love using the example of Harry Potter and magic because, I love Harry Potter, don't get me wrong. But magic can't exist because it breaks the laws of physics because it creates energy out of nothing. So they say a spell, right? They say Wingardium Leviosa, and the object rises in the air and it dances around, and things just happen, or full people disappear. It takes energy to do that. And clearly, that's what magic is. It happens without reason. So she explains it once in the book and said, it takes the energy from everything around you, and that's how it works. Which is a good way to kind of explain it. But anyway, Harry Potter and most magic violates the laws of physics. But, you gotta have some fun, so, you can't judge all those type of things. So let me just digress this and talk a little bit about what this means, in my words. Those were like the textbook words. So it means that the total mechanical energy at any point in a system, and I'll define that in a second, will always be the same as long as no outside work is present. It's kind of like the first law of Newton's first law. Objects in motion will stay in motion unless there's an outside force. Energy will be conserved unless there's work done. It's kind of the same idea. So what I mean by system is a big word in physics for the scenario that you're studying. Oh boy. This is being recorded here. Spell these words right. Scenario, right? Yeah. Okay. Scenario. So, what do I mean by a scenario? So, for instance, I can have a skier on a hill. It's a terribly steep hill. This is the black diamond, right? Like this is a danger ski zone. This is the expert ski slope, okay? So the scenario would be the skier on this hill. So the total mechanical energy here, I'm going to make up a number just to use as an example. Say it's 50 here. Will have to be 50 down here. That's what I mean, assuming there's no work, i.e. friction or pushing. If you have friction, it takes away energy, and if you have somebody pushing, you add energy. If I was a skier on that slope and decided to say, nope, I'm going to go faster, what am I going to do? Take my skis and push, right? That makes me go faster, I've added energy. This is a skier just saying, just going down without pushing themselves. Yeah.
What happens if they like push off? Does that count?
Yeah, that would count. Well, let me answer this in this way. If you're pushing, you're adding energy. So this would not conserve energy. So if you, for example, I'll do the example in blue. Say you push yourself. You know, the skier pushes themselves. What happens here, and you can kind of guess at what happens. You might start with 50 joules of energy, but would you end with 50?
No.
What would you end with?
However much you push.
Yeah, so you're adding energy. So is it going to be more or less than 50? More. I'm going to make up a number. You got it. So that's with positive work. What do you think is going to happen if you had negative work?
You're pushing yourself backwards?
Like friction.
Would that be slowing down?
You'd be slowing down. So if I start off with 50 joules of energy, would I end with 50? What would you end with?
25.
25, sure. You get the idea. You have less energy. You've already got the concept. This is conservation of energy. If you have no work, the numbers stay the same. If you add work, you increase your number. If you take away work, you decrease your number. That's the big concept here. But I'm going to show you a bunch of other things that kind of explain this concept.
So you took negative work.
Not necessarily. A good example, so let me just diagram that. With free fall, it's actually going to be no work. Well, actually kidding. Sorry. Free fall, your force is down because gravity's pulling you, right? And then your distance is also down. That's positive work. That's because as you fall down, you gain speed. You're speeding up, so that's an additive work. Sometimes I answer questions too fast, sorry. That's a speed up.
So, like, if you give us an example like that, it would be positive work.
Yeah.
Because of the speed up.
The speed up and the direction are the same. Not so much that they're down, but they're pointing the same. Like on your homework, for example. Exactly. Alright, so let me show you a few things. I like this animation. This is basically your lab. So what you're seeing here is a roller coaster. You can see it, going through the loop, going up and down. Notice that it's showing you, this is a bar graph, and it's showing you the types of energy and how much kind of conceptually. They don't actually have numbers here. So as you might imagine, potential energy is based on height. So notice that's the highest at the highest point. And then as you're on the ground, notice it goes away. Because you have no height, you have no potential energy. Vice versa, every time you have a lot of motion, you have the highest kinetic energy. This is total mechanical energy. What do you notice about this bar the whole time? It's the same. This is conservation of energy. In fact, it also implies that there's no work because this stayed the same. So this is specifically in the absence of friction or pushing. So also, what's more important is it's the total energy. If I add this plus this, I get that. And notice that they balance out the whole time. If one goes down, the other goes up. In fact, if you add these at any point, they'll be the same value. That's conservation of energy. So, and then I could write it mathematically. The initial energy has to equal the final energy. That's all that means mathematically. I for initial, F for final. I'm actually going to skip this one and go to this one. I make my point several times today. So this is the same scenario, but now you have numbers to kind of back that up. Notice that the total energy is 50 over here, which means that that's got to be the same. It's 50 here, 50 here. You get the point, right? Every location, the total. That confuses people because sometimes you say, well, yeah, the energies are actually changing, and they are. The individual energies will change, but if you add them up, they will stay the same. So just careful with that. That can be confusing sometimes. So let me show you too your lab. So your lab is going to be, you're going to go to this online lab. It's pretty fun. You go to a simulation, this site. You've done labs on this site. This one is this guy. So it's Tony Hawk Skate Park. There we go. I'm going to add the friction one in here because I want to show you what friction does. You can kind of guess already. Alright, so when you're doing this lab, some helpful things is why I'm also videoing this. So if you forget, you can use the video. So when you're doing this lab, click on the bar graph. It's just like the one you just saw. The grid is really helpful because it gives you the heights, so potential energy. And then it's just nice to see the speed if you want. You don't need it, but I kind of like it. I'm going to actually right now take out friction. So no friction. Okay. So if I put the skater right at 5 meters exactly, so I'm reading 5 meters right on that line. We can see that the skater goes back to exactly 5 meters on the other side. Do we see that in real life? No. We see this case, right? And then that skater will kind of dance a little bit. So anyway, let me talk about what's going on here. So I'm actually going to take friction back out. Actually, I'm just going to reset everything. Start over. So first of all, notice that there's no energy in the system because the skater is not moving, nor is the person lifted in any way. There's no height, so there's no energy. It's not there because it's starting, it's because it's literally no energy. Now, in order for me to actually put the skater up here, I have to lift him up. I have to push him. If I push, that's a form of work, right? So when I push him, I actually add energy to the system, and you can see that when I lift him.
Oh.
See how the total energy changes now?
So why is it potential?
Because I'm changing his height.
Okay.
That's the idea, so height and potential. So this is adding work to the system because I have to push him up. But as soon as I put him on here and let him go with no friction, the total stays the same. No friction. I'm not pushing him now. He naturally will go down. And there's no friction, so there's no work in this case. So no work, no change in this energy. And however many energy I have here is what I have here. So it's nice because it's very predictable. If you have 5 meters on one side, you're 5 meters on the other side with no energy loss. But when I do put friction in, you already know what's going to happen. He slows down. But what happens is that the energy goes into something else. So it's still conserved, but he doesn't get the energy. It goes into the ground. So if he can't get all the potential energy, it doesn't go into his motion. It goes into the ground, so he slows down. So it's another way to think about why things slow down. Because the energy goes out of him into something else. And in fact, that's what this shows when I put friction on. You can see a rise in thermal. Now they call it thermal here because Actually, friction is when you heat something up. Like, it's like if you take your hands and do this, you can get warmer. You're moving the atoms here, and that's a form of thermal energy. So it's going somewhere else. It still conserves the value. It just leaves the skater. That's why he loses energy here. This is work done against it. You lose energy like that. Your lab is essentially looking at these properties. Kind of what I said. You're going to look at what, you're going to lift the skier up. You say what increases, the skier goes down. The energy of his kinetic energy increases. You're going to make these observations and some calculations with that. Okay.
So friction is interchangeable with thermal?
Yeah.
Okay.
Yeah, for the lab. Yep.
So does thermal energy come from, like, moving your hands? Like, does that energy come from, like, where does it come from?
Yeah, so it's work, right? Because I'm pushing.
Yeah.
So that work, so that energy, what makes me do this is from the food that we eat.
Okay.
We actually conserve, we have to conserve energy. So, in other words, every day we have to eat because we expend energy every day. That's why we eat, because we use up the calories that are in food, and we have to replenish that food every day. So that's how energy works with your body. Okay, so I want to show you this because it's kind of like a puzzle, but using that idea again. So I'm actually going to pause the video in a second because I'm going to have you work on this exact question. But here's the puzzle I want you to figure out with you and your table. If you notice, I left some blank for you. Maybe something you'll see on your quiz. Maybe exactly what you'll see on your quiz.
Can you link this? Can you link this? So we can practice that one.
What's that?
Can you link this?
Yeah. It's in the PowerPoint,
Oh.
and you can see the video too. So, okay, so I'm going to give you a major hint here, okay? Notice that some of these are blank.
Oh, I got it.
Notice that some of these are blank. So you need to figure out the total mechanical energy of the system first to find this out. The biggest hint is that I do give you those two values that you need to figure it out, but you need to find that first. Then I want you to fill in the blanks for me. I'm just going to number them just so you and I can be on the same page. We'll just number them. Oops, sorry. Sometimes this is finicky. Come on. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9. See if you can figure out the pattern. And then, just like you saw on the Energy Skate Park, we have these bar graphs, okay? Now, they don't have numbers, so it's fine. It's just relative. Just estimate here. But I want you to figure out how much energy you have in the kinetic and the potential at location, for example, A. Go with the locations. B is actually here. And then tell me what the total mechanical energy is for the system. And I'll tell you there's no work here. So we have it conserved, okay? So I'm going to pause the video for a second so that you can figure this out, and then we'll discuss the answer in a second. Okay, so this is how you approach a problem like this. Now, as you notice, there's a bunch of ones that are missing here, but in order to figure this out, kind of like we saw before with the other skater, we had two numbers to work with. They always had to be the same. So we need to find a point where we have two numbers that can tell us what the total is. I hope you notice, and hopefully you notice that you do have that right here. Did anyone notice that?
Yeah.
Okay. So the total mechanical energy has to be what value? 40,000. By the way, the energy is measured in joules. That's the J. Okay, so that's what the J means. Okay, so with that said, everything has to add up to 40,000. So that it doesn't actually matter where you start, so I'm just going to start here just because it seems like a logical place. Notice that we have no energy in motion here, kinetic energy. It means it's at rest here because it means because this is 0. But this plus this must equal 40,000, so the total potential energy has to be 40,000 right here. Everyone comfortable with that? 0 plus 40,000 gives you 40,000. And then here we go. So right here you have potential energy is 20. It has to equal to 40, so this also has to be 20,000. I'm going to skip these for a moment. This has to be 15,000. This is 3,200. What? 32,500. And then this one is 35, right? 100. That all looks okay?
Yeah.
Okay, everyone follow me with that? So then the question is, oh boy, we have 2 blanks here, right?
Yeah.
So how do we figure that out? I'll give you 2 methods. The first method is to recognize you're at the bottom of this hill. So we can pretty much assume that the height here is 0 meters. Go ahead, yeah. So if you have 0 height, you're going to have 0 potential energy. So no energy associated with height if you're on the ground. So if that's 0, then this must be 40,000. That's one way you can think about it. The second way you could think about it is notice that this is actually the same location as D, and this one, this doesn't have a label. So you could also say, oh, that's 40,000, 0, then this is the same location, 40,000, 0. 2 ways to figure that out, whichever way works. If it's on the bottom, yeah. Usually the case is 0 potential energy, all kinetic. That's usually the case. Okay, so now for the bar chart, how you figure out something like this. First of all, make sure you pick the right location. I remember I was solving this one of the first times, and I did B right here, and actually B's right here, so just be careful with that. So at location A, we're at the top here. We have no kinetic energy. So I usually just put a little line there on the bottom, just to say that I considered it, and it's, I didn't leave it blank, so it's 0 there. And because this really doesn't have any numbers, I'm just going to say it has all potential here. And then if I add kinetic plus potential, I get all here. In fact, technically, all of them should be filled up. That's the first thing I would do if I were you on a test. I would fill all these up first, because that has to be true because of this condition. Coloring is fun. Okay. All right. So location B, they're halfway, so you would color them in roughly halfway. I'm not going to, measure this. Oh, you're a centimeter off of halfway. It's wrong. I'm not going to do that. I'm going to look at it since you got the idea. Location C, notice you have more kinetic than potential, so same thing. I'm going to give 3 blocks to kinetic and 2 blocks to potential. A little more kinetic than potential, but more importantly, they add up to 5 blocks. Okay, that's important. You can't have 6 blocks and 6 blocks and say that this is 5. That doesn't work. So they have to still add up to the total blocks that you have here. I think there's 5, right? Yeah. 3 and 2 equals 5. Location D, we have no potential, all kinetic. And then E, tiny bit of potential, a lot of bit of kinetic. Okay. Get the idea on how to fill those in? Okay. Moving on. 2 more things. Notice that this is the same thing, but there's one added dimension to this, is now they want the height and velocity at each of these locations. So I'm actually going to do the first part really quick. I'm going to ignore the bar charts because I'm assuming you'll be fine with that. I'm going to fill in the missing information really quickly. So 10 joules, 0 joules, so it has to equal to 10 each time. 2, so this has to be 8. This has to be 10. This will be 10 and 0. Everyone okay with how I got those numbers?
You got 10 0 because those 2 the first one and the last one at the same height.
Exactly.
Okay.
It's a pendulum swinging, so at the very end of the pendulum it stops for a second. So that's why it's 0 kinetic. Then it swings down. You have the most energy at the bottom with kinetic, and then you come back up. So, yeah, I did that really quick. But yeah, that's exactly why. So, I might ask questions like, what's the height and velocity? The way to do that is you're going to use the equations. Kinetic energy is equal to 1/2 mv squared. And then the gravitational potential, GPE, they use PE here, but these are related, is mgh. So for example, if I want to find the height at this location, I need the potential at that location. I'm going to do it up here because I don't have much room. But PE is this equation. The energy is 10 joules. The mass is 2. I had to get that from here. G, yep. H. See how that works? So you're solving this equation. I'm going to do it quickly. You can't see any of that. So sorry. I'll do this for a quick moment. That's better, right? Thank you. I didn't recognize that.
Okay,
G is 9.81. So when I calculate the height of this, I get 0.51 meters. Does that make sense? Do you want to see a kinetic energy done, or are you okay?
No, thank you.
Okay. So the important thing is height goes with potential. Velocity goes with kinetic. So if I want to find the velocity, I need the kinetic energy. So the kinetic energy is 1/2 mv squared. Now you can't see that one. I'm going to post these online too, so all my notes you'll have. So 8 joules is the kinetic energy at this location. 1/2 the mass times v squared. So I'm solving for v squared when I do this. Actually, if you notice, the 2's cancel out, right? 2/2. So 8 joules is v squared. What do I need to do? So the square root of 8. Yeah, it's like a 2 something, right? Oops. 2.82. And that's associated with that one right there. Okay? So that's how you could do like a next step to this. I think you might have a homework question on this, so I wanted to go over how you would go from the bar chart to the calculation. All right. So the last thing I want to do is actually show you how work does affect a system. That's what this worksheet is, okay? We're going to look at work now, adding or taking away energy. This is on your midterm. This is why I'm videoing this too. This is literally on your midterm. Well, it's going to be one of these, not all of them. Notice that this paper is also online, energy bar charts. Okay, so I'm actually going to show you 2 examples, and then I'm going to have you work on 2 examples, okay? I'm going to show you a condition with work, and then a condition without work, okay? So you can understand how these work. Notice that they're different than what we used before because now we can go negative. Notice that we can go negative now. Honestly, the only thing that's going to go negative is work. The only thing that's going to go negative is work. Because you can either add work or you could take away. So negative work or positive work. So I don't even know why they actually add, these parts, but they do for that reason. So the first one, I'm going to show you that we have a ball that starts at rest. It falls. And we're looking right before it hits the ground. So not the part where the ball actually stops, but right before it hits the ground. So there's no work in the system because it says ignore air resistance. So it's a way of saying no friction. So no work here. It'll actually say work in the problems. So this is no work here because it says ignore air resistance. So if we analyze the system, we started at rest, so there's zero kinetic and all potential, exactly. We have the maximum height, no work, so that's 0. So remember that these have to add up, so 0 blocks plus 5 blocks plus 0 blocks has to equal 5, exactly. But where does the 5 go? Does it go into kinetic or potential? So that's a good question. Where, you know it has to be 5, but where does the 5 go?
Oh?
It'll go to kinetic because once the potential's at the bottom, there's no height, so then the kinetic has to be it, and also once you like go down, like it's gonna be the fastest.
Okay, so look at the scenario. You're at rest and your final state is moving here, right? You're also, if this is potential's based on height. What's the height at the bottom? 0. So though right before the bottom. Right before, yeah. Yeah, so we have no height here. So that's going to be 0. And then it'll be all kinetic. See what we're doing? Now, notice the bottom right here is exactly what I'm doing with mathematics, even though it looks really complicated, but the initial kinetic plus the initial potential plus the work has to equal the final. I'm doing this mathematically right here. Okay, so that's with no work. The next one has work on it. This one right here. A car skids from a high speed to a stop when the brakes are applied. The initial state of the car is traveling at a high speed, and the final car is at rest. The force of friction does work on the system, thus changes the total energy. So it physically tells you that. Exactly. So, you can kind of see, so interesting, right? We start off at a high speed. I'm just going to make up a number because I'm a visual person. Let's say it's going 100 meters per second. And then it says it stops, so it goes to 0. So notice those two things. Secondly, what's the height initial?
0. It's on the ground.
It's on the ground. What's the height final?
0.
Exactly. There's no height change, so there's actually going to be no potential in each case, right? So these are actually both 0 automatically. I actually like to do the potential first for this reason, because usually it's pretty straightforward. There's no question if you analyze the heights. So no potential there. So let's give it a highway speed. So it has lots of kinetic to start with. So my pen's starting to die, so that's why it's a little shaky. Okay. So I have lots of kinetic, no potential. But before I fill in the work, what do we know about the velocity at the end?
0.
What does that mean by the kinetic energy? 0.
Wait, why is it? Oh, 0 because it stops moving. Okay.
So if this is plus 5,
Into the ground.
has to be negative work. Exactly. So this goes here instead. So notice that we have positive energy from the motion, and then friction takes away that energy. So this is negative 5, sorry, it looks kind of weird, let me fix it.
use the numbers that we have, like the 100 meters per second, the kinetic energy will be 100, and then the work will be -100?
Almost, because this actually needs, this is just a velocity, you would need mass to 1/2 mv squared.
Okay.
But yes, if you find the energy of that, it would be the same energy of this. You're right. So notice here that friction is taking away energy. It changes the total energy of the system, right? The total energy went from, this is the initial and the final, right? The total energy initial was greater than the final. That's because there was energy taken away. Yep.
Kinetic energy is -5 because it's starting moving. I mean, it's starting and then goes to stop.
Why is kinetic energy not 0?
Like not filled in from 0 down
Oh, because
it's starting.
the 0 mark is here in the middle. So it's a positive value.
It's not. I was just thinking because it's negative work, it has to be negative. Because it's starting moving and then going to a stop. So is that why the kinetic is?
Oh, I understand your question. You're right, it's slowing down. We model that not through kinetic, we model that through work here. And that makes it negative. That's where the negative goes. You're right, the slowdown is important. That means negative work. So not the positive part. Okay, so coming back to the conservation of energy, if the energy changes, then there was work involved. So this is relating that idea. So this is where you have work here. Let me show you actually, just because we're running out of time, I want to show you positive work, how that looks when you see it as positive work. If we have time, I'll have you do a few. If not, the solutions are online. I recommend that you think through these and see how you do with this. I know I'm not going to have time today. Let me show you one more. This one. You have a skater starting at the top of the hill, and she now uses her poles to push her across. Thus, she's adding work, she's changing her energy. The initial state is on top of the hill at rest, and the final state is on the second hill at B. Ignore frictional forces. So we're not having any work against, but we're going to have work added because of the ski poles being pushed. So let me just underline that, because that's the positive work right here, sorry. So I'm going to just think through this out loud. So first of all, I know the person's at rest at the top, so there's 0 kinetic. And then because they're at the, they have a very high hill here, I'm just going to assume it's all potential. Why not? You could actually just choose to start at 4. It's still fine. It doesn't matter as long as your relative values are the same. I'm actually going to hold off on work for a second. So it doesn't say we're at rest here. We're actually still moving here, because it doesn't say otherwise. So we'll have some form of kinetic. We're also at a lower hill. What would you say? Is that half or 2/3? What do you think? Half? Alright, so I'm going to do the potential first. So we have half here. Halfway filled. So remember, these have to equal each other. Now, first of all, we do work to actually push ourselves. So I'm going to add, let's see, I'm going to do this for a reason, a half, 2.5 here. Because I have to have 0 plus 5 plus 2.5. This is 2.5. So what should the kinetic be?
5. -5.
Should be 5. Because this side, 5 plus 2.5, should be the same as 5 plus 2.5. See where I figure that out? Hopefully it makes sense, because when I add work, in this case, the person goes faster. I've added work to the system. If I didn't add work, the person would have gone slower. They're going faster than they normally would without pushing.
So where does the work go?
Into her speed.
Oh, okay.
Into her speed. I'm assuming it's her.
How do you know, like, to have the work? Or you kind of just do it so it balances?
You do it so it balances. So counter, another example. If I said, I'm going to make it 3 because it's easier, then I would add 3.
Okay.
But you just balance it out. There's no set numbers here. It's all conceptual. Yes?
So when we have like word problems like this, are you going to give us numbers, or are you just going to give it just like this?
Just like this. Just like this. On your midterm, I'm literally going to give you a question like this, where I'm going to ask you to either do it with work or without work. You'll see it on your midterm review, exactly like this.
So if we don't get these numbers exactly, is there
No, so if you said, okay, potential is 4 instead,
yeah.
and you made this 1, I'm sorry. I'm looking to see that this side is balanced.
Okay.
So if you made this 4 and 1, it's balanced. I'm looking for balance. Like that. Okay? Any other questions? Great. Well, that concludes this video on conservation of energy.